and 9, you do the same calculation, and sequential over random comes up to 33 to 1. And what this means is you can't afford to move the heads. Everything you got to do has to be, if you're going to use that water pipe, little bitty water pipe that you have effectively, you got to do sequential, 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 and you got to read as little data as possible. So these, this is driving database systems to avoid using non-clustered indices, doing sequential scans, and reading as little data as possible. Now, the next thing I'm going to do for a while is I'm going to turn to CPU trends before I go and look at software solutions. So here's sort of the VAX architecture. There's a CPU. There was a very small L1 cache. There was no L2 cache. The L1 cache was used for both data and instructions. But the two things to look at are how many cycles per instruction. It was like 10. Today's processors are, 1 instruction every cycle. But the important thing to think about is that it was about 6 to 10 cycles to access memory. So it was very balanced between how fast the processor ran and how fast you could get at memory. Now, I couldn't possibly draw a Nehalem. My PowerPoint is not good enough to give you a Nehalem with split memory, quad core. So those CPUs are meant to be, those are really cores, and the whole die is the CPU, et cetera. But now we have 2 levels of cache or 3 levels of cache. We have private caches for instructions and data at the L1 level. We have shared caches at the L2 level. The processor runs about 1 cycle per instruction because it's all doing all this out-of-order stuff that the architects love to do. It's 2 cycles to access the L1 cache. It's 20 cycles to access the L2 cache. And memory is out like in Peoria. Memory is 200 cycles away from the processor. And you can only run really effectively if you use those L1 and L2 caches and get a lot of hits on those caches. Now, so as I pointed out earlier, memory accesses relative are much, much slower. And the cache line size is typically only about 64 bytes. And I'm going to show you some slides that next that show how these factors have affected performance. Ooh, that didn't work. Oh, I'm sorry. I thought that was going to work. So the thing up in the upper right-hand corner, I changed the color at the last minute. That's a citation for a paper a former graduate student of mine wrote that was published in 2005. These results are from IBM DB2 running on Linux. The SQL Server results I have are older, and I'll point out the differences. There's an Intel Quad CPU, P3, Xeon, and those are the. And we took the TPCH queries running on a 10 gig database with a 1 gig buffer pool. Now, there are 2 sets of queries over which we've computed some averages. The scan-bound queries are a bunch of TPCH queries that are bound by the time to do the scans. The join queries are TPCH queries that are constrained by the join execution time. Along the x-axis, or the y-axis, we have normalized execution time. And the thing I want you to look at is this is where the processor is spending its time. So that's what these. So there are few people in the world can actually look inside the processor when a database system is running and say, what the hell is it doing? So Natasha is one of those people, and she's really a fantastic architect. So the blue stuff at the bottom is useful computation. That's when the CPU is actually doing something at all useful. The red stuff in the middle are memory stalls. So if you look at it, like 50% of the time, the CPU is sitting there waiting on the memory to deliver something into its caches. And it's slightly bigger for scans than joins. And again, this will vary from database system to database system. But the pattern is similar. Then the green stuff is branch misprediction stalls, and the top thing is resource stalls. But the red stuff is what I want to drill in next. So these are the memory stalls. And this is the breakdown. So if you dive into that red bar, you get some different kind of stalls. You can get translation buffer stalls, L2 data cache stalls, L1 data cache stalls, et cetera. And what I want you to look at now is the big green bar. So of those memory stalls, which again, normalized execution time on the y-axis, 50% of the time spent waiting on memory. if you look at why it's waiting on memory, it's waiting on memory because the L2 data cache is stalled waiting for a transfer. And it's like, of those memory stalls, 90% of them were L2 data cache stalls for the scan queries and 30-some% for the join queries. Those, the red on the, it's interesting, the red on the join queries is really DB2, a DB2 artifact. Those instruction cache stalls on the join-bound queries can actually be filtered out by clever compiler techniques. And SQL Server does much better at getting rid of that red stuff, but that just means it has more green stuff. So, and again, it's what the architects have done to us. They've put us as database researchers and developers into this awkward corner. We have to work around their product designs. So the L1 instruction cache stalls, partially how the database are architected, partially how good the compiler is, whether you do code read organization. And as I said, SQL Server does a lot better. The L2 data cache stalls are an artifact of how we've built database systems for the last 30 years. And it's a layout that the database community calls a row store. And it's just an old name it's what you're familiar with. So here's my table. So now I'm going to do a few animations here because I haven't done any animations. So I've got this row store layout, and I've got this table, and the thing on the left is what I'm going to load, okay? So I start loading the table, and I take the rows that are getting loaded, and I pack them into pages, and I store them on the disk drive on the right. And you know, if the rows are a couple hundred bytes long and the pages are 8K bytes, you know, you'll get about 40 of those per page. But basically, you take every row that's being loaded, and you put it on the data page, one after another, with some other fancy indirection mechanisms called the slot array at the end. But basically, the rows are stored as, like, you would expect them to be stored. Turns out that's not the only way, and we'll come to that. This is a standard way we've been doing things since the very beginning, since the first relational database systems were built in the mid-70s. Okay, now here is, and I hope you can read this, here is an attempt to explain why there were so many cache stalls. So I'm going to go back, wait a minute, I'm just going to go back here. So the cache stalls are those green things. The green things, when cache is stalled, the CPU is stalled for the most part. That's not totally true, but the green stuff is bad. But why do we have so much green stuff? And this is an attempt to try to explain that. So at the top, I have a very simple CPU. It has, that's the die, it has a CPU, it has 2 cache lines of L1 cache, 4 cache lines of L2 cache, and a main memory buffer pool with exactly 2 pages. And I know we have big, gigabyte buffer pools, and L2 caches are megabytes, but you get the idea. So down there on the disk, I've got a database which has exactly 3 pages in it, and every page holds exactly 3 rows. So you see it's some kind of customer table, and I've got Bob there, and Bob's balance due is $3,000, and Sue's balance due is $500. Now, when the database tries to run that query, select ID, name, and balance due from customers, where balance due is less than $500, greater than $500, what happens? Well, the database system fetches the page into the buffer pool. You know all about that. But then, in order to apply the predicate, balance due greater than 500, the balance due field for every customer must migrate up through the cache hierarchy. So there's Bob's balance due plus some other bytes around Bob. Okay, cache lines are always transferred on 64-byte boundaries. So the database, the architecture says, we need to bring these bytes in the L2 cache. Then they go into the L1 cache, and Bob's a winner. Okay. He's got a big balance due. He's going to get a nasty letter. Then we have another cache miss when the next record gets processed, assuming that we're not doing cache prefetching. And I'm going to get across the idea. Then an L1 cache miss. We bring up 500, then bring it up 1,700. So we process all the records on the page, and basically, for every record, we essentially will get an L2 cache miss and then an L1 cache miss. And then we'll bring the next page into memory, and then we'll have a whole bunch of misses. And we'll bring the next page into memory. And you can just see, as we bring in pages and process the rows on each page, we have to bring the relevant attribute values into the caches so we can process the query. Now, for this example, I read 3 pages from disk, and I suffered perhaps up to 9 because I had three pages, 3 records per page, 9 attributes I had to process. I might have had as many as 9 L1 and L2 cache misses. And that's why there's all that green stuff in those L2 data cache stalls that we saw a couple slides ago. Now, and remember that if we have to stall the CPU, if we can't do anything else, if the prefetch doesn't work, the CPU isn't used. And that's why at that first performance slide you saw, the CPU was that blue bar at the bottom, doing nothing while we're running this query on DB2. So this is sort of a row store summary. When we're running queries on a row store or a conventional relational database system like SQL Server, we can incur up to 1 L2 data cache miss per row if the row size is bigger than the cache line size. And this is mostly true, okay? The database system transfers the entire row from disk to memory, even though the query only needed 3 attributes. Remember, the query was ID, name, balance due. Maybe 20 or 30 bytes out of the 200 bytes. But because we laid things out as rows on those database pages, we have no choice but when we transfer the page to transfer all the attributes of all the rows on every data page. Remember that 10,000x, 65x deal? Big water reservoir, small pipe, transferring stuff I don't need, attributes that I don't need to execute the query. Factor this bandwidth is really, really, really precious because it's only gone up a factor of 65 in 30 years, whereas capacity's done this 10,000. And there's an alternative organization that is actually a very old organization, first proposed in 1970, and it's called something called a column store. Now, you heard a little bit about this when Casey talked about Vertipack, and I'm going to try to explain it from a slightly different point of view. So here again, I have that same customers table. Okay, I've got ID, name, address, city, state, balance due. But instead of loading the pages full of rows, I'm going to sort of transpose things. And I'm going to store all the values in the first column in a file by itself. And then, so here you see I've taken the ID column, and I've taken this table, and instead of slicing it horizontally and packing stuff on pages, I'm going to slice it vertically and pack every column tightly on pages in the database, and then put them all together in a file. So you can see all the ID values are stored together in one file. Then the names are extracted, and all the names are stored after one another in pages on a file. And the IDs all fit on one page. The names took 2 pages. So there you can see Bob, Sue, Ann. Then I do addresses. Addresses are bigger, so I need 4 pages. You see little 4-page things there to hold the addresses, and then cities, and then states, and then balance due. So instead of, it's a very simple idea. As I said, a very old idea that is now gaining popularity. Instead of storing things row-wise, I store things